Hello, this is Mr. White, and this video is on differential equations and slope fields. Here is the one exercise for today, although it is a multi-part exercise. It is intended to look similar to free response questions on slope fields that one might see on an AP exam. And I'll point out that typically free response questions on regarding slope fields are non-calculator questions. Part A has us by hand sketching out a slope field for the given differential equation. Let's just review real quickly the process for constructing a slope field. I strongly recommend making a table. Now, given that the indicated points represent 1, 2, 3 x values across and 1, 2, 3, 4, 5 y values up and down, we'll make our table accordingly. 3 columns across and 5 rows up and down. Exactly, something like that. And let's go ahead and label these for x values, -1, 0, and 1. And it looks like the y values here go from -2 to 2, so -2, -1, 0, 1, 2, those are y values. So we will use this differential equation and the respective x and y values to fill in the table. I would probably start by looking at the equation and thinking of what values are going to make our job easiest. If we notice that any time that x is equal to 0, it doesn't matter what y is, that dy over dx is automatically going to be 0. So whenever x is 0, which is this entire column, right, we know that the dy over dx will automatically equal 0. Similarly, if I look and see what y value is going to make this dy over dx equal 0 every time, well, it looks like any time y is -1, it doesn't matter what x is, the dy over dx will be 0. So we know that we're going to get slopes of 0 in this row as well. So let's start filling in the remaining non-zero values. Looks like when x is 1 and y is 0, I'm going to get 1 times 1, or 1 right here. If I make x equal to -1, then up top I'll just make this -1, and that means my dy over dx is the negative of what it was over here. In fact, we can pretty quickly sense that all of these values over here are going to be the opposites of whatever these values over here are when you look at the equation. So if I go back to just making x equal to 1 here, and I bump my y value up by 1, so now y equals 1, 2, I see that I get 1 times 2, or 2. And if I bump the y value up again to 2, I get 1 times 3, which gives us a 3 here. If I bring the y value down to -2, I get 1 times -2 plus 1. That's going to give me -1. And again, since all the values in this column are going to be the opposites of the values in this column, I fill in accordingly. All right, for the slope field itself, the easiest thing to do is start again with the zeros. So we notice that for all these values where the slope is going to be 0, let's draw little horizontal line segments. Again, that's where y is equal to -1. And we're drawing horizontal line segments because these little segments have slopes of 0, right? And let's next turn our attention to where we have slopes of 1. We notice that at both of those points, if we have a rise over run of 1, I'll draw a little line segment like that. And I'm visually in my head, I'll go ahead and draw it here, but I just recommend in your head you connect the dots. You say, okay, that looks like a rise over run of 1 over 1. Similarly, when you draw the line segment through this point, connect it in your head to that point where there's going to be a slope of 1 over 1. So something like that. Again, with your eyeballs extending it and saying, yeah, that looks like a slope of 1. Okay, we'll take a similar approach with these values. They should both have slopes of -1. So here, and in my head I was trying to aim for that point right there, which would give them slopes, each of those slopes of -1. All right, how about this one here? That's slope of 2. That's going to be this point right here, and if it's going to have a rise over run of 2 over 1, that means this rise of 2 and this run of 1 also have it heading for that point right there. So I'll draw a little line segment. In my head, it's aiming towards that point. All right, this value over here, slope of -2, it's also aiming towards that point. It seems like all our slopes in this problem are aiming towards that same point down here. That certainly won't always be the case in every slope field problem where they all aim towards the same point, but it sure is here. Again, for a slope of 3 up here, rise of 1, 2, 3 over a run of 1, indeed has it headed for that point. So if I'm visually, or in my head, connecting the dots, I'll draw a line segment like that. And finally, oops, that's this point over here. We'll draw that in. And that is our slope field. Now, what does that do for us? Well, notice that we haven't done any calculus really. We haven't done any separation of variables, and although we will find out later in the problem that it is possible and we'll be asked to do so here, there are some times where separation of variables is impossible to do. So this might be, at this level of calculus, your best bet, is to draw a slope field and at least you get a visual sense of what the solution curves might look like. We get the sense that if we wanted our solution curve to pass through this point here, we could say, okay, there's going to be a horizontal tangent line right at that point. But as I go to the right, these curves are suggesting that it starts to swerve upward. And the curve should always be running parallel to and even tangent to those slope field line segments. Never would a solution curve cross like that. Never would they cross perpendicular like that. They're always running parallel between the slope field segments, kind of like this, or even tangent to the slope field segments. So if we had wanted the solution that ran through that point right there, we could tell that it's going tangent there, but then it's going to sweep over, and then it's going to be whisked down like that, or something of the sort. Again, slope fields are not for high precision mathematics, but it just gives you a visual sense of the graph. Okay, let's go on to the next part, part B. And you'll notice that I've copied the differential equation down here as well. While the slope field in part A is drawn only at the indicated points, it is defined everywhere in the xy plane. Describe all the points in the xy plane for which the graph is concave up. First, let's take a second to just think about what that's asking. When you think back to some of the little example solution curves that I was drawing just a moment ago in blue up here on the slope field, you might recall that some of them were, that one of them was smiling, the other one was frowning, and we can imagine there are many more that are smiling and frowning amongst those. So it sometimes throws students off when they're asked to describe the points for which the graph is concave up in this case. Students sometimes wonder, are they looking for words? Or are they looking for equations? It's really kind of flexible. And let's just start by thinking of what does concave up make us think of mathematically from a calculus perspective? Should make us think of second derivatives, right? So even though you may have a sense of how to describe where your solutions are going to be concave up and where they're going to be concave down, even if you can do it in words, you definitely want to back it up with some actual calculus. So let's start by taking our second derivative. All right, in this case, since we have a function of x times this function of y, we're going to use the product rule in finding second derivative of y with respect to x. So product rule says second function, y plus 1, times the derivative with respect to x of the first one, 3x squared, plus the first function, x cubed, times the derivative with respect to x of the second. Now that's going to be 1 plus 0, right? 1. But since we're taking the derivative with respect to x, implicit differentiation, aka chain rule, says we need the dy over dx there. Okay, so that's step one of finding our second derivative. What are we going to do with this, dy over dx? Well, we've got an equation over here, and we're going to substitute in this for that dy over dx. So x cubed y plus 1. Okay, notice that there is a common factor here. There are two terms here, 1, 2, and both have an x squared. Over here we actually have x to the 6, but the common factor would be x squared. And both have a y plus 1. Y plus 1. So let's put some big parentheses here. And we'll put a 3 on the inside, because 3x squared, y plus 1. This term is all accounted for, plus x to the 4th, because x squared times x to the 4th gives us x to the 6, and here is x to the 6, times y plus 1 times y plus 1. This term is all accounted for. All right, now that's our second derivative. What is it we're supposed to do with that? Well, let's remind ourselves. We are looking for where this graph is going to be concave up. So we need this second derivative to be concave up. We need it to be greater than 0. All right, so let's look at that second derivative one factor at a time. Let's start with this one here. So you notice that it doesn't matter what x is equal to. If x is positive, negative, or 0 itself, this will always be positive. This factor underlined right here. This will always be positive. So that's not going to have much effect on our second derivative as far as changing its sign. Let's look at this one next. We need this to be positive. Well, almost the same is true for that, x squared. That is almost always positive. There's only one exception. If x is equal to 0, that renders this whole left side equal to 0, and this inequality would not be true. So we can say that based on this, we cannot let x equal 0. Okay, so with that exception, x being 0, if this is always positive, and other than x being 0, this is always positive, that means that this middle factor has to be positive as well. So let's write the inequality. Y plus 1 has to be greater than 0. And that's the same as saying, if I subtract 1 from both sides of the inequality, that's the same as saying y has to be greater than -1. So how would I describe all the points that on the graph where this graph is going to be concave up? I would say graph is concave up for all x not equaling 0 and y greater than -1. And I would put a box around that one. So let's connect that with what we did in part A. Here's the line y equals -1, and again, all the points above it, other than where x equals 0, these points here, it does appear that we have a bunch of smiling portions of the graph. We do get the sense that this graph is going to be smiling, concave up, concave up, concave up. But notice it is important that we made that distinction, that right at these center points right here, that technically the graph is not concave up right at the y-intercepts. And sure enough, anywhere below the y equals -1 line, we're going to have frowning graphs, concave down graphs. Okay, so as I said, even if you kind of saw that coming from part A, you still really need to get used to showing the algebraic / calculus backup for your answer. All right, finally, find the particular solution, y equals f of x, to the given differential equation with the initial condition f of 0 equals 2. Well, this was a problem similar to this recovered in the previous video, so I'm going to go through this at a little quicker pace. Remember, this is just our separation of variables process. So let's start by getting x cubed and dx on the right side of the equation, and we'll get the dy and the y plus 1 over here on the left. So our variables are separated. We'll integrate both sides, and on the right we'll get x to the 4th and a 1/4 in front. And we typically put the plus c on the side with the x's. And then over here on the left, we see our u prime over u mold. So we'll put ln absolute value y plus 1. Let's see, how do we get rid of that ln on the left-hand side? Well, we use its inverse, the exponential function with base e. So we make both sides exponents of e. On the left side, at least, the e and the ln cancel each other out. We get y plus 1 absolute valued. On the right side, recall, as shown in the previous video, we'll use our exponential properties. If I've got e to the something plus something else, I can break that up into e to the first something times e to the second something. And let's call that C1 in both places. And I repeat, I'm going through this quickly, but if you're having trouble following, check out the last video. Recall that if you have a constant e raised to another constant C1, we're going to define that and call that C. And just see if I can keep this all on one screen here. Let's go up here, and we have y plus 1 in absolute value bars equals, and I'll put that C in front now, C times e to the 1/4 x to the 4th. I presented an argument in the last video arguing absolute value bars on the left-hand side are equivalent to a plus or minus on the right-hand side. So we'll put the plus or minus c e to the 1/4 x to the 4th. But I also then followed up with an argument that said, since c here represents any arbitrary constant, positive or negative, the plus or minus was redundant. So in actuality, we can do away with the plus or minus in this particular context. We subtract 1 from both sides. Bam! Don't you wish you could make answers appear that quickly? And before we go on to find our particular solution, let's take a quick look at Geogebra, where I've got that general solution entered in. As well, as you can see, there's the slope field, similar to what we drew earlier. Now notice right now in that general solution, I've got a c value of -3 right now, which I will change. And you can see that as I change the c value, the particular solutions creep up onto the screen here. We're seeing those solution curves. And what I'd like to do is I'm going to bring up an even denser slope field there. So same differential equation, but I've just got little line segments filled in at more points on that plane. And as I sweep through some different c values again, notice again that at every single point, let me zoom in even a little bit. At every single point along the curve, it is running parallel through and tangent to those various slope field segments. So it doesn't matter what c value I have, it never crosses the slope field perpendicularly. It's always running parallel and tangent. Okay, so coming back to this problem here, we want to find the particular solution that satisfies f of 0 equals 2. So let's plug in 0 and 2 for x and y respectively. Now this entire exponent becomes 0, and e to the 0 power is just going to be 1, and 1 times c would just be c. Minus 1 equals 2, so clearly c equals 3. And it doesn't look like I'm going to quite make it on the screen. That's okay, I'll scroll down, and we'll put y equals 3, our new c value, e to the 1/4 x to the 4th minus 1. And that is our final answer. And just to make absolutely sure that it is correct and that it agrees with everything else we've done, let's go back to Geogebra one last time. I'm going to put that initial condition on the screen. There it is, that magenta point at 0, 2. And let's change the c value. Let's bring it all the way up to 3. And we see that is exactly where it passes through that initial condition. So, final answer.